Hello, welcome to another episode of Maths in an Empty Classroom with me, Mr. Southern. This is part one of the lesson on further differentiation applications, and in this video I'm going to be looking at finding a turning point and a tangent to a curve that is consisting of the product of two more complicated functions. So here we go. The curve C has equation y equals e to the 3x sine 2x for x values between 0 and pi over 2. We're being asked to find the x coordinate of the turning point on C for which x is greater than 0. And then in part B, we're being asked to find an equation of the tangent to C at the point where x equals 0. Okay, so we are being asked to find the turning point. Crucially, we're just being asked to find the x coordinate. We'll deal with that when we get there. But for a turning point, we need to differentiate the function to find dy dx and then equate that to 0 and solve. So my original function, y equals e to the 3x sine 2x. I have the product of two functions here. So what I'm going to do is call the first one u. So u equals e to the 3x. And I'm going to call the second part v. So v equals sine 2x. And I'm going to differentiate this using the product rule. So u equals e to the 3x. That means that du dx equals 3 e to the 3x. So remember, when we differentiate exponentials in e, the e bit stays the same, and we multiply by the differentiated power. And then dv dx, so differentiating sine 2x, we're going to get 2 cos 2x. That's because sine differentiates to cos. Using the chain rule, multiply by the differentiated bracket, if you like. So 2 cos 2x. Right, the product rule then is that dy dx is equal to v du dx plus u dv dx. So what I'm going to get for this function here then, dy dx equals v, which is sine 2x, multiplied by du dx, which is 3 e to the 3x, plus u dv dx. So u is e to the 3x, and dv dx is 2 cos 2x. Okay, so let's just tidy that up a little bit then. So my expression for dy dx is going to be 3 e to the 3x sine 2x plus 2 e to the 3x cos 2x. So that is my expression for dy dx. To find the turning point, or a specific turning point we're going to find here, I need to make this equal 0 and solve to find x. So here we go then. So we have 3 e to the 3x sine 2x plus 2 e to the 3x cos 2x equals 0. So what I'm going to do first, I'm going to factorise the e to the 3x term at the front of the bracket, giving me 3 sine 2x plus 2 cos 2x equals 0. So I have the product of two things equaling 0, but e to the 3x equals 0 has no solutions. There are no values of x for which e to the 3x equals 0. So I can just proceed with this second bit, which is 3 sine 2x plus 2 cos 2x equals 0. People get in a right old pickle with these, particularly if they know the double angle trig identities. What you just have to spot with this is you have sine and you have cos, and you have sine and cos of the same function, in this case 2x, which means we can use the identity tan equals sine over cos. So to enable that to happen, I'm first of all going to write it as 3 sine 2x equals negative 2 cos 2x. And then I'm going to manipulate that so it's sine 2x over cos 2x equals negative 2 over 3. What that then means is I have sine of a function over cos of the same function. I can use the identity to give me tan of that same function. So tan 2x equals negative 2 over 3. And I then need to solve this to find the value of x. So 2x is going to equal tan inverse of negative 2 over 3. Make sure you're in radians mode. Which comes out as negative 0.588, etc., etc. Now, just an important thing here, a couple of clues in the question. The first one, it says find the x-coordinate of the turning point on C for which x is greater than 0. So I'm not there yet. I'm told originally that the curve is only defined between 0 and pi over 2. So even though this is solving the equation, it's not solving the model. So what I need to do is I need to think about tan. Well, tan is going to repeat every 180 degrees or every pi radians. So I need to add pi to this value here to get a second value for 2x. So if I add pi to that, I'm going to get 2.553, etc., etc. And crucially, that is 2x. So to find the value of x, I just need to divide that by 2, which is 1.276. So to 3 significant figures, x is 1.28 radians. Just referring back to the question again, I underlined this at the start and said I'd talk about it when it became relevant. The x-coordinate of the turning point. I do not need to substitute back in to find y, because I've only been asked for the x-coordinate. Right, part B is saying find an equation of the tangent to C at the point where x equals 0. So, all the information that I have then, I know that x equals 0, I know that y equals e to the 3x sine 2x, and I also have an expression for dy dx, which I'll use in a moment. The two things I need to find the equation of the straight line are a point and the gradient. So the first thing I'm going to do is substitute x equals 0 into this equation to find the point on the curve. So y equals e to the power of 3 lots of 0 multiplied by sine 2 lots of 0. Well, e to the power of 0 is 1, but sine of 0 is 0, so 1 times 0, my y-coordinate is 0, which means the coordinate that I'm finding the tangent for is actually the origin. The other thing I need is the gradient, so I'm going to substitute x equals 0 into my expression for dy dx. I'll just remind myself what that was. 3e to the 3x sine 2x plus 2e to the 3x cos 2x if memory serves. Yeah. Plus 2e to the 3x cos 2x. Okay, so if x equals 0, we're going to get 3e to the 3 lots of 0 sine 2 0 plus 2e to the 3 lots of 0 cos 2 lots of 0. Right, so e to the 0 is 1, so I'm going to get 3, but sine of 0 is 0. 2 lots of e to the 0, so 2 lots of 1, that's going to be 2. And now cos of 0 is 1. So that is going to give me just 2, which means that my gradient is 2. It's going through the origin, So the equation of the tangent to the curve at that point is simply y equals 2x. Gradient 2 going through the origin, y equals 2x, which I think is quite neat. So there we go. Join me in the next video where I'll be looking at a similar type of question, but when x is defined in terms of y. I'll see you then.